Hello everyone, and welcome. I'm excited to kick off this presentation on electricity and its concepts. Today, we'll explore the fundamental ideas behind electricity, from basic principles to how it impacts our daily lives. We'll cover key concepts, important theories, and some practical applications. So, let's get started and discover the fascinating world of electricity together. Let's take a closer look at the idea of electrical energy and power. Electrical energy is the energy that is carried by electric charges as they move through a circuit. It's what powers our devices, from lights to computers. When we talk about power in this context, we're referring to the rate at which electrical energy is transferred or converted into other forms of energy, like heat or light. Understanding how energy is transferred helps us design more efficient systems and troubleshoot issues effectively. Throughout this presentation, we'll see how concepts like electric potential difference and resistance influence the flow and efficiency of electrical energy in circuits. Now, let's talk about insulators. All nonmetals, except for graphite, are insulators. This means they cannot conduct electricity because they lack free electrons between their atoms. Insulators are materials that do not allow the flow of electricity through them. On the other hand, all metals are excellent conductors of electricity. Interestingly, graphite, which is a form of carbon and the only nonmetal that can conduct electricity, also falls into this category. They can conduct electricity because there are free electrons moving around between their atoms. Materials that allow the flow of electricity are called conductors. This flow is essentially electrons in motion. The discovery of electricity is credited to William Gilbert, who was one of the first to understand this phenomenon. So, in summary, conductors have free electrons that enable electricity to pass through easily, while insulators do not. Understanding these differences is key to grasping how electrical systems work and are designed. Let's start by understanding the direction of electric current. By convention, electric current is said to flow from the positive terminal to the negative terminal of a power source. However, when we look at electrons, they actually flow in the opposite direction, from the negative terminal to the positive terminal. This might seem a bit confusing at first, but it's important to remember that the conventional current direction is just a historical convention used in circuit analysis. Now, what causes this flow of electrons? The device responsible for generating this flow is called a cell, which is essentially a source of electrical energy. When we connect two or more cells in a row, we call the entire setup a battery. So, whether it's a single cell or a battery, they both serve to produce the movement of electrons. Electric current itself is essentially the flow of these electrons through a conducting material. Materials like copper or iron are good conductors because they allow electrons to move freely. This movement of electrons is what we measure as electric current. Speaking of measurement, the symbol for a unit of electric charge is C, which stands for coulomb. The coulomb is the SI unit used to quantify electric charge. To visualize this, think about rubbing a glass rod with a silk cloth. After doing so, the glass rod can attract small paper particles. This ability to attract small objects indicates that the glass rod has acquired an electric charge. In summary, electric charge is a fundamental property that can be transferred or accumulated in objects. And understanding how charge and current work together helps us grasp the basics of electricity and how devices operate. Electric current is measured using an instrument called an ammeter. When we talk about the SI unit of electric current, it's called the ampere, symbolized as A to give you a sense of what that means. 1 coulomb of charge flows through a conductor in 1 second when the current is 1 ampere. Now, mathematically, we express electric current as the rate at which charge flows through a conductor over time. That's represented by the formula I equals Q divided by T, where I is the current, Q is the amount of charge in coulombs, and T is the time in seconds. So, in simple terms, electric current tells us how quickly charge is moving through a wire or any conductor, and we measure it with an ammeter. This concept ties into the overall theme of understanding how electricity works, especially how we quantify and measure electrical flow efficiently. Let's talk about electric potential difference. It's essentially the work needed to move a unit positive charge from one point to another. Think of it as the energy required to shift a small positive charge within an electric field. The SI unit for this potential difference is called voltage. Represented by the symbol V, you can measure voltage using a device called a voltmeter. Now, mathematically, voltage is expressed as the work done, W, divided by the amount of charge, Q, that's moved. So V equals W over Q. This means that the higher the voltage, the more work is done to move the charge. Electric potential itself is a bit different. It's about the ability or capacity of a charge to do work when moving a unit positive charge from one point to another. It's like the potential energy per unit charge at a specific location in an electric field. Understanding these concepts helps us grasp how electric energy is transferred and how devices like batteries and circuits operate efficiently. So, in essence, potential difference is about the energy transfer needed to move charges, and electric potential reflects the capacity of a point to do that work. Let's take a closer look at how a chemical reaction inside a cell creates a potential difference between its two terminals. This difference essentially sets electrons in motion, which in turn produces an electric current. Think of it like a push that gets electrons moving through a circuit. Now, the potential difference you see in a circuit is usually provided by a cell or a battery. They act as the source of this voltage, creating that essential push for electrons to flow. But here's a key point. Electric current will only flow through a conductor if there's a difference in electric potential, what we call voltage, between the two ends of that conductor. Without this difference, electrons have no reason to move, and the current simply won't flow. So, for current to happen, we need that potential difference to be present. That's why the conditions for current flow depend on having a voltage source, like a cell or a battery. It's the fundamental principle that drives our entire electrical system. Let's talk about the resistance of different materials. When a material has low resistance, it allows electric current to pass through it easily. In contrast, high-resistance materials oppose the flow of current more strongly. Now, how are these materials connected in a circuit? Low-resistance materials are typically connected in series with other components, meaning the current flows through them one after the other. Next, I want to introduce the ammeter. An ammeter is a device we use to measure the amount of current flowing through a conducting material. It's an essential tool for understanding how much electrical current is moving through our circuits. Moving on to circuit components, you'll often see devices like voltmeters, ammeters, variable resistances or rheostats, resistors, electric bulbs, and switches. For example, a switch can be in a closed position to complete the circuit or open to break it, controlling the flow of current. Now, regarding resistance again, high-resistance materials are connected differently, typically in parallel, across the ends of the conducting material. This setup allows us to measure voltage, which is the potential difference across those ends. A voltmeter is the device used here. It helps us understand how much energy per unit charge is being transferred across that part of the circuit. Finally, I want to briefly describe what an electric circuit is. Think of it as a continuous, closed path that allows electric current to flow from the power source, like a battery or a group of cells, through various components such as bulbs, resistors, and switches, and back again. This closed loop is what makes electrical devices function smoothly. Here, the constant R stands for resistance for a given conductor wire at a specific temperature. Resistance essentially measures how much a material opposes the flow of electric current. When we talk about resistance, we're looking at how difficult it is for electrons to pass through the wire. The equation V equals I times R, or V equals IR, shows this relationship clearly. It tells us that the voltage across the wire is proportional to the current flowing through it, with resistance being the proportionality constant. Now, Ohm's law states that the current flowing through a conductor is directly proportional to the potential difference between its ends, as long as all the physical conditions, like temperature, material, and shape, remain the same. So, if you increase the voltage, the current increases proportionally, provided resistance stays constant. This fundamental principle helps us understand and predict how electrical circuits behave under different conditions. It's a key concept that ties into the overall theme of understanding electrical properties and their influence on circuit performance. Let's consider a simple example to understand resistance better. If the potential difference across the two ends of a wire is 1 volt and the current flowing through it is 1 ampere, then we say that the resistance of that wire is 1 ohm. This relationship is actually the basis of Ohm's law, which states that the resistance is equal to the potential difference divided by the current. The SI unit for resistance, therefore, is the ohm, symbolized as omega. Now, resistance is essentially a property of a conductor that determines how much it resists the flow of electrons through it. In other words, it's like a measure of how much a material opposes electrical current. This concept is fundamental because it helps us understand how different materials behave in electrical circuits. Remember, resistance isn't just a random property. It's a key factor in designing and analyzing circuits, ensuring that devices work safely and efficiently. So, understanding resistance helps us see how materials and components interact with electric current, which is at the core of all electrical technology. The SI unit of resistance is the ohm meter, symbolized as omega. Now, here, rho, which is the Greek letter for rho, represents the resistivity of the material. Resistivity is essentially a constant of proportionality that tells us how much a specific material opposes the flow of electric current. Think of resistance in terms of the material's properties and its dimensions. The resistance R is proportional to the length L of the conductor divided by its cross-sectional area A. So, if you increase the length of the wire, resistance goes up. Conversely, if you increase the cross-sectional area, resistance decreases. It's important to note that resistance isn't just about the physical dimensions. It also depends on the material itself. Different materials have different resistivities, which is why some conductors are better than others. Temperature also plays a role here. Resistance increases as the temperature of the material rises, which is an important factor to consider in practical applications. Overall, understanding how resistance depends on these factors helps us design circuits that are efficient and reliable. Now, let's look at how resistances add up when resistors are connected in series. The equivalent resistance, which we call Rs, is simply the sum of the individual resistances R1, R2, and R3. So Rs equals R1 plus R2 plus R3. In terms of voltage, the total voltage across all these resistors is the sum of the voltages across each resistor individually. That means V equals V1 plus V2 plus V3. An important point to remember is that, when resistors are in series, the current flowing through each resistor remains the same. This is a key feature of series circuits. So when 3 resistors, R1, R2, and R3, are connected across a power source labeled OB, they form a series connection. This configuration is common in many circuits, and understanding how the resistances and voltages add up helps us analyze and design these systems effectively. Let's take a closer look at this slide. The first key point is the formula for the reciprocal of the equivalent resistance, which is written as 1 over Rp equals 1 over R1 plus 1 over R2 plus 1 over R3. This tells us that when resistors are connected in parallel, their combined resistance isn't just a simple addition, but rather calculated through the reciprocals. Now, moving on to the current, the next point is that the total current I flowing through the entire parallel circuit is actually the sum of the currents through each resistor. So I equals I1 plus I2 plus I3. This makes sense because in parallel, the current splits up across the different paths, and the total is just the sum of all those currents. Another critical concept here is that the voltage across all these resistors remains the same. Regardless of their individual resistances, they all experience the same potential difference when connected in parallel. To put it all together, when we connect three resistors, R1, R2, and R3, in parallel across points A and B. These principles apply. The overall resistance decreases because the current has multiple paths to flow through, and the voltage stays consistent across each resistor. Understanding these key points helps us grasp how parallel circuits behave, which is fundamental to analyzing more complex electrical systems. Now, let's talk about the units used to measure electrical energy. The SI unit of electrical energy is the joule. Abbreviated as J, you might recognize joules from other areas of physics, but here it's specifically used to quantify the energy consumed or produced in electrical systems. There are a couple of important formulas to keep in mind. One way to express electrical work, or energy, is W equals V times I times T, where V is voltage, I is current, and T is time. Sometimes you'll see it written as W equals I squared R times T, emphasizing the role of resistance in energy consumption. Another way to look at it is by considering the charge Q, which equals I times T in that case. Electrical energy can be expressed as W equals Q times V essentially. We're multiplying the charge that flows by the voltage across the conductor to find the energy used. It's important to understand that electrical energy is essentially the work done to keep the current flowing through a conductor. This is fundamental because it links energy consumption directly to the work required to maintain an electrical circuit's operation. Understanding these concepts helps us grasp how electrical systems work, how energy is transferred, and how to calculate the energy involved in various electrical processes. This knowledge is key to designing efficient electrical systems and managing energy consumption effectively. Let's start by understanding what power means in an electrical context. When an object has a power of 1 watt, that means if we have a current of 1 ampere flowing through a conductor across a potential difference of 1 volt, this amount of energy transfer is happening every second. In simple terms, power tells us how quickly electrical energy is being used or transferred. The SI unit for power is the watt. Symbolized as W, it's a standard measurement, just like meters or seconds, but specifically for energy transfer rates in electrical systems. Now, there are a couple of formulas that help us understand how power relates to current, resistance, and voltage. One of them is P equals I squared times R times T, which shows how power depends on current, resistance, and time. Alternatively, power can also be expressed as voltage times current, P equals V times I. Finally, we can think of electric power as the rate at which electric current is being used. It's like a measure of how fast electrical energy is being consumed or supplied in a circuit. This concept ties into the overall theme of understanding how electrical systems operate efficiently and safely. Let's take a closer look at the relationship between a kilowatt-hour and joules. So, 1 kilowatt-hour, or 1 kWh, is the amount of energy consumed when 1 kilowatt of power is used for 1 hour. Now, since power is in kilowatts and time is in hours, we can convert this into joules, which is the SI unit of energy. We know that 1 kilowatt equals 1,000 watts, and 1 hour equals 3,600 seconds. Multiplying these together, 1,000 watts times 3,600 seconds gives us 3.6 million joules, or 3.6 times 10 to the 6 joules. This conversion is important because it shows how the energy we use in everyday life, measured in kilowatt hours, relates directly to joules, the fundamental unit of energy. And this is why the commercial unit of energy is expressed in kilowatt hours, because it's a practical way to quantify large amounts of energy consumption, especially in electricity billing and energy management. Understanding this relationship helps us connect the abstract concept of energy to real-world applications and ensures we're all on the same page when discussing power and energy. Let's talk about heat energy, denoted as H, which can be expressed as I squared R times T now. This relates directly to the power and energy involved when electrical current flows through a resistor. We also know that power, P, can be written as the work done over time, or W divided by T since work is the energy transferred. It's also equal to voltage times charge, or Q times V. Remember, according to Ohm's law, voltage V equals current I times resistance R. Combining these, we see that power can be written as V times I, which makes sense because voltage and current are the driving factors for energy transfer. When a current I flows through a resistor R for a time T, the charge Q that moves through the resistor is equal to I times T. The work done in moving this charge through the potential difference V is essentially the energy used in the process, which manifests as heat energy. So the work done on the charge, W, is equal to Q times V. This shows us that the energy transferred to the resistor is directly proportional to the charge and the potential difference across it. In summary, this slide ties together the concepts of work, heat energy, charge, voltage, and resistance, illustrating how electrical energy is converted into heat when current flows through a resistor. This is fundamental to understanding how electrical devices generate heat and how energy transfer occurs in electrical circuits. That's it, folks. We've reached the end of our presentation. I hope you found the information both insightful and engaging. As we wrap up, I want to emphasize the key points we've covered today. First, understanding the importance of the main concepts is crucial for applying what we've learned. Second, the connections between these ideas help us see the bigger picture and how each part contributes to the overall theme. And finally, remember that the goal is to take this knowledge and use it effectively in your own work or projects. Thank you for your attention and participation. I appreciate your time and look forward to seeing how you implement these ideas moving forward.